give Ed as much time as possible, so we'll get back into it. Don't forget the signal report. It's on your tables and by the door. Just give us a little feedback on what you think and what you want to see from the club. Ed Fong was first licensed in 1968 as WN6IQN. He later upgraded to Extra when 20 words per minute was required with his present call of WB6IQN. He obtained Bachelor of Science and Masters of Science in Electrical Engineering from the University of California at Berkeley and his PhD from the University of San Francisco. He is a life senior member of the IEEE. He has 13 patents and over 50 published papers and books in the areas of communications and integrated circuit design. Presently, he is employed by the University of California, Santa Cruz as an instructor teaching graduate classes in antenna design, RF design, and high-speed interface. And without further ado, I'll give it over to Ed.
Oh, he's muted.
Ed, you're muted.
Oh, yes, there. Okay, now you should hear me.
Yep.
That was you, Adam? Is that you, Adam?
Yes, sir.
Okay, very good. Oh, why don't you turn on your camera for the Delta Club?
You're just going to see me, but...
Oh, really?
Well, turn it around.
All right, turn it around. Face the audience. But, there you go. Wow, that's a big group. Oh, man, that's a huge group. How many folks? Wow, you've got about 20, 30 folks out there?
43.
43.
Well, I better give you a good show then, right? Okay, here we go then. So let me see if I can share the screen. And then we can get started. Very good. Excellent. Okay. Okay, so let's see, I can share now, right? Yeah. And you should be able to see that. You see that, right?
Yes.
Yep.
Very good. Okay, thank you very much. And then where are you guys located?
Memphis, Tennessee.
Oh, in Memphis, Tennessee. Okay, right in the Midwest. All right, anyway, like what happens, my name's Ed Fong. I teach over at UC Santa Cruz. But tonight we'll talk about antennas. This will take about 40, 45 minutes. So prepare for that. So let's get started. This is the first of several talks I give. This is one of the more straightforward ones in which we take a single band antenna and we make it dual band. And how do you do it and how do you do it correctly? There's a lot of ways of doing it. How do you do it correctly and based on what we see, this method works quite well. This method I'm going to show you tonight, I think we first published it back in 2003, the basic fundamentals of it. We've made improvements here and there, but it's in the ARRL handbook and Antenna Classics, the Antenna Volume 8 Compendium, Volume 3 Compendium. So it's pretty well understood and pretty well accepted. This is the article on the right on the original one. This is the roll-up version that we did, and then the last one we did was the tri-band version of it. How do you make it 2 meters, 220, and 440?
Recording in progress.
All in one pole. That was my daughter in her younger years. She's KJ6QXM. She's got a master's in mechanical engineering, bachelor's in mechanical, and also a master's in robotics. So we get to talk on this. How do you make a tri-band without affecting your performance? That's pretty popular. And also, we hold 2 patents on this. Not that we didn't hold more. The antenna I'm going to talk about tonight, we did not patent. I just didn't think of it back 20, 25 years ago, I figured. Come up with a cool idea, publish in QST. If people like it, they can try it. Well, it turns out the only problem with that was people liked it, they started building it, they started selling it. They started selling it under my name, but it's still okay. I think where it really tipped it was when we started buying some of these that I didn't build. They claimed, here, buy the Ed Fong antenna, and they didn't work very well. They didn't actually understand the article of the details of how to tune it and all that. They weren't tuned, they were all in the commercial band, some in the weather band, all over the place. And to get it to work dual band, both VHF and UHF, is actually quite hard. We have to read the article in detail and really take it step by step in the tuning. So after that, we started patenting it just to protect ourselves. So we did an article on how you get gain out of a J-pole antenna. In other words, how do you make it into a collinear, two-element collinear? We patented that, and it's all done by our school attorney, Michael Kaufman. He's K6 VCD, this is called his hand. And we also did the tri-band. So I give a talk on how to get gain. That's like a 30-40 minute talk also. Good principles, how do you get gain out of that collinear? And how do you get the third band, 220. This tri-band is a 2 meter, 220 and 440 all in one. But today we're going to talk about how to just dual band an antenna. So if I'm going to dual band an antenna, the first thing to say is, well, what kind of antenna should I choose? Well, this is about 20 years ago, and by that time, I think, well, we were using a lot of ground planes, but this idea of an end-fed J-pole started becoming popular. I didn't know a whole lot about it, but my friend Denny Monticelli introduced me to it, and it's actually quite a good choice. It has no radials, and the problem with radials is that they break off. It's more cumbersome stuff. So with no radials, get really good high wind load resistance. Also, a vertical J-pole has a very good ideal dipole pattern, 360 degrees, fairly low angle radiation. And it's also end-fed. What's interesting about it, when it's a dipole, the angle radiation is a little bit lower than a ground plane, a few degrees. And what does that result in? It actually results in about 1 to 1.5 dB of gain in the horizon. So for all intents and purposes, you're talking to other people at the horizon. It gives you 1 to 1.5 dB of gain, a little bit of gain. And I'll explain that in a while why. See, what's interesting is I took this picture a few years ago out in Mount Sutro, out in the Bay Area. That's one of the big towers here. You could tell it's one of the big ones. Commercial, mainly police and fire on this one. But it's interesting. I took this picture, I brought it home, I downloaded it, and said, what's interesting? None of these antennas I can see have ground radios anymore. None. There's a beam here, sure, for probably some link. But in terms of the verticals with ground planes, no ground planes. And I know 30 years ago, if I had taken this picture 30 years ago, most antennas would have been ground plane type antennas. So even the industry trend has gone to, I think, you get tear them apart to probably J-pole type design. And why did they do that? One thing, no radials, as we mentioned. So, because when you have radials, they just stick out, and the horizontal force coming down, vertical force from the horizontal radials, just it's not overwhelming, but it's heavy. Now, I'll give you an example of this. You guys can see the video. Here's an example. If I were to hold up an antenna vertically, it's easy to hold up, much less there's just vertical force. But once you exert a horizontal force, make this into a horizontal force like this, it's much harder on my hand, much harder to hold. And over time, if you have 3 radios sticking out in the mountain like this, mountaintop, 100-mile-per-hour winds in the wintertime, they just break off. So it's best not to have anything stick out. Also, I'll show you in a J-pole, you don't need a lightning arrestor. It's a DC short by design, and I'll show you this in a while. So if anyone tries to sell you a lightning arrestor, $40, $50, and you're already using a J-pole design, convince them you don't need it. You just don't need it. Okay. See, other antennas we've tried years past is just a conventional dipole. And that's basically a J-pole. It's a vertical dipole, but it's end-fed. Why do you want it end-fed? Because again, nothing wrong with a vertical dipole, not electrically, but physically, you gotta feed it at 90 degrees. When you gotta feed it at 90 degrees, that means you gotta hold it up with some mass. So from a mechanical point of view, it's not very good. Ideally, if you want this dipole to work well, you gotta stick it way out in the open, way out in the air, with the coax at 90 degrees so it doesn't interfere with it. But how are you gonna hold it up? The torque at that point is gonna be tremendous. And, you know, we, about 40, well, probably 50 years ago now, we played around with building these things. And you put them on mountaintops, they work fine until winter passes because we just soldered them just like this. We didn't weld them, man, people weld it. 20 years ago, I didn't know about that. I had a blowtorch. A blowtorch just melts solder. Solder, as you guys know, is very soft. It gives you an illusion it's metal, but it's a very soft metal. And what happens is if you just rock this back all winter, it'll crack and eventually comes off. It's not designed to be rocked back and forth, not soldered. So this is a dipole antenna. It works well, but physically it's hard to implement. It doesn't last very long. We had to replace these after 4 or 5 years. In windy areas, it just didn't work very well as repeater antennas. So back to the J pole. The J antenna, I got introduced to it back in the 1990s, late 1990s, probably, by Denny Monticelli 86C. And this is a big trend of making them out of 300 ohm twin lead that you buy at Radio Shack. You know, $3, you go 50 feet and you can build a couple of dozen of these things for next to nothing. So that was a pretty good idea. And so I took one home that they built and I tried it out and yeah, it works quite well. And I noticed it was better than the ground plane. And why is it better than the ground plane? Let me tell you why. A simple explanation. A simple explanation. Yeah. Well, I guess I can explain it from here. Simple explanations. A vertical dipole, which this is, part of a J-pole, just take this part, a 37, 38 inch part. That's the halfway dipole. You center feed it in a dipole. Okay, let me take this here. Center feed, that's dipole. Gives a pretty ideal pattern. What is causing the waveform to be lower angle radiation? What causes it to come down the wave and not horizon? It's the other piece, the other quarter wave piece. It's 180 degrees. So it's pulling quite hard, which makes the wave lower angle radiation. If it were a ground plane, it isn't 180 degrees. It might be 45 degrees, it might even be 90 degrees if it's on top, using a car top as your ground plane. Then it doesn't pull as hard. And you'll notice, maybe I should plot this sometimes, do an easy night plot. You won't see it as flat. In fact, here, I can show you a plot. It's gonna happen. Here's a good plot. This is just a fundamental dipole. It's a fundamental dipole. If it's a dipole, it looks like this. This is sea level, this is the sky, and this is the earth. So this is in free space, this would be the bottom, this would be 0 degrees, and this would be space. So this is an ideal dipole. A vertical, like what I showed. Nice pattern, figure 8, and you figure you're standing here, you're talking to your friend here, walking down the street or whatever, out in the ocean or whatever. It's a pretty nice pattern. But that's because what pulls this pattern down? It's the other quarter wave. It's this other quarter wave. The problem is if this was the ground plane with radials, it isn't pulling it as hard. So what happens, let's go back here. What happens is in a ground plane, it won't look quite like this. This will be lopsided, going up slightly. I mean, ever so slight. It's a few degrees. I mean, it's not like the thing won't work, it'll work. But if you measure it, that lobe goes up a few degrees. So you lose about 1 to 1.5 dB because of the angle. In other words, this peak here, max, is winds up about here instead of there, about 1.5 dB. So that's another thing I favor about this J-pole that we're going to use. So then he gave it to me, and it was just in a roll-up form. I put the coax and put it on HD, and it worked fine. I thought about it, this antenna works quite well. I think we've got to redesign it, put it into a PVC pipe, put a SO239 connector on it, and we got some. And sure enough, that works pretty well. I also made a dual band, and that's what we're going to discuss here. But we've sold well over 35,000 of these now, and really good performance. PVC pipe these days, the new stuff, UV protected. It's cheap, very durable. You can pick it up at Lowe's. It's convenient. So that's what my group here at UC Santa Cruz, we build it, and that's how we raise our funds. In fact, you see the workroom in back here. They come at least twice a week, and we just go away cutting wires, cutting stubs, soldering stuff. I ultimately, I put them all together and I tune them all. And why do I do that? We do build them in class, but only onesie twosies as a lab exercise. But in production, I can't have the students really put it all together and test it. Because I only get my students for like at most 2 years, 3 years. And so by the time they're defective or I see a defect, it comes back to students log on. So what I do is I put them all together. I put them all together, I write all the customer receipts and everything. So ultimately, if you have a problem with it, it's always my fault. I'm like the end guy. Buck stops here, basically. So anyway, how do you make a dual beta? Well, what's interesting is the basic J-pole. I think a lot of you guys probably have these or have built them. You make them out of 300 ohm twin lead. You can also make it out of copper pipe, version of this. But if you make it out of twin lead, it's pretty straightforward. You get a piece of twin lead, about 60 inches tall. You notch it here, you notch it there, so that the half-wave dipole exists from here to here. So half-wave at 2 meters, 37, 38 inches, depending where you want to resonate. So in a normal dipole, you would have fed it in the middle, just like that picture I showed you before. Why? Because that's the low impedance point. It's the high current, low voltage. In the ends of a dipole are high voltage, low current, which means they're high impedance, which means you can't feed a coax to it directly. You can feed a coax to it directly in the middle, but then it's 90 degrees, and mechanically it's just too cumbersome, it won't hold up. But if you can get it in this configuration, and this is the J-pole configuration, with high impedance at the end, then you just have to match the high impedance. Match the high impedance to your 50 ohms. Turns out that's not so difficult. Because on a Smith chart, the Smith chart says if you have a short circuit transmission line, 0 ohms, short circuited, it can be 300 ohms coax where it doesn't matter. If you short circuit it, and you move it 1/4 wavelength. 1/4 wavelength in the case of 2 meters for twin lead, about 15, 16 inches. Coax will be a little shorter. It will be an open circuit. Similarly at UHF, you start with a short circuit, I have one right here. A short circuit quarter wave stub, it's only about 5 1/4 inches or so. If you short circuit it here, it's an open circuit there, AC wise. And you know, my students are always intrigued with my dad, because what do you mean, Ed? You short circuit at one end, shouldn't it be a short circuit on this end? It is only a DC, but as you put an AC wave on it, you go quarter wave, it will be an open circuit. And similarly, if you have an open circuit, you go quarter wave, it will be a short circuit. And I know a lot of folks have a hard time, you RF guys experience hams. You've seen this, but if you're just coming from a DC background, DC circuits background, it doesn't seem to make sense. And I tell them, the thing you've got to get through your head, I think one thing is AC and DC, they almost operate opposite. DC meaning DC circuits, AC meaning RF waves, radio waves. And I tell them one way I can convince you that they're totally different is that, you know, if I gave you a block of wood, is that an insulator or is that a conductor? Well, most people would say it's an insulator. That's correct, a DC block of wood. But clearly at AC, when there's a radio wave signal, it conducts, because radio waves go right through your house, goes right through wood. So it's the direct opposite. And then I give a similar argument if I give you a piece of aluminum foil. Is that a conductor or is that an insulator? Well, a DC is clearly a conductor. But we use that as a Faraday shield in signals, RF signals. So it blocks RF signals. It blocks RF signals. So it's almost directly the opposite. So that's almost like one thing you've got to get straight now. You come to my class, break apart that AC and DC. One Smith charts and propagation, Maxwell's equations. The other one is DC Ohm's law. Don't get the two confused. Now let's go back here. So, I started taking this J pole that I showed you, standard J pole. How do you make it dual band? This is a VHF, these are dimensions for VHF, but we would like to make it also work at UHF. Well, what's interesting is, by the early 2000s, HROs, if you went down to HROs, and you wanted to buy a handy-talkie, they were trying to convince you at this point, rightfully so, why go spend $200-300 on a single band handy-talkie? For about $50 more, you can get a dual band handy-talkie. Why not? Get UHF. Because 20-30 years ago, UHF repeaters started cropping up because all the 2-meter repeater channels were taken up. And so they convince a lot of people this. They start buying, by then, why buy a single band, just add $50 more, get a dual band. But what about an antenna? Of course, they probably tried to sell you an antenna too for another $200. Well, knowing hams, they're going to say, well, I'll think about the antenna first. They go home and they try the 2-meter ground plane, maybe a J-pole at the time, and they said it actually kind of works. And I mean that, it kind of works. It doesn't work, it kind of works. Kind of works meaning that the SWR seems to be okay. And you RF antenna guys, HF guys, that you can use a 40-meter antenna up to 15 meters. It works. It won't blow up your radio. It may not be the pattern you want, but it works. That's because antennas always behave in a fashion that they resonate at their odd harmonics. That is, I built you a 100 megahertz dipole, and you got the little nano in one of these cool little nano VNAs here. I hope most of you guys have here for under $100 to steal. Can't afford not to have them in your hand these days. If you took a 100 megahertz dipole, put it on a nano, and you see, hey, it dips at 300, 500, 700, etc., until it hits other limitations, losses, or whatever. But if it doesn't hit that, it will resonate at its odd harmonics. So 100 will be 300, 500, 700, 900, etc. So what happens at 2 meters? 145 megahertz. Well, if you multiply that by 3, well, 45, 440. So when you put it on your bird block meter or whatever SWR meter you have, it doesn't look that bad. In fact, the good news is it won't blow up your radio. It's good enough, certainly, where it shouldn't blow up your radio, for sure. So a lot of hams start using it. Well, it doesn't, because the first thing you always check for an antenna is the SWR, just to make sure. Whether it works or not, if the SWR is low, at least it won't blow up your radio. So people start using it, but they quickly noticed, it doesn't work real well. And they were asking me, why doesn't it work real well? But at least it resonates. Well, if you analyze it, if you do a vertical antenna, 2-meter ground plane, and you put it on its third harmonic, which is UHF, you lose about 6 to 8 dBs in the horizon. You get this. Vertical dipole, 2 meters, exactly like what you want. This is a really nice pattern because not only that, vertical dipole creates a null vertically. This is the sky. You're not talking to an airplane. You're not talking to an International Space Station. It's really ideal. Most of your energy goes out in both directions in horizontal. But now, I said, if it's a vertical dipole, you have it on 2 meters, it will also resonate at UHF. It does. Except that when you start simulating on an easy network, just trying it out, it doesn't work real well. Good reason. Because the blue line here, you look at the pattern. Not too good. You're standing here, you're transmitting on a vertical dipole tuned to 2 meters. But you're operating now at UHF. Turns out only about 25% of your energy goes in the horizontal plane. So your partner's sitting here, you're trying to talk to them. Well, unfortunately, about 75% of your power is going up into the sky at 45 degrees angles. You're only left with about 25%. There, it's about 6 to 8 dBs. You're clearly, unless you're talking to a strong repeater, you quickly notice, hey, there's something wrong here. SWR is good, but performance is pretty poor. So, that was my task when I talked to folks back 25 years ago. can you make this an antenna or a modification of an old antenna, like a J-pole, make it truly dual band? So I took on that challenge. But it's an interesting challenge because could you probably make a dual band antenna? You can do anything to get enough money. All else fails, go buy one. But the goal is, can you make it simple, reproducible, so some people can actually do it at home and still be rugged? You know, without having fancy components, you can't, because it's going to stand in the air, the wind blows in the winter, blows it apart. It's going to be simple, durable, and cheap. So the conclusion I had was, if you were to make this thing dual band, you cannot buy any inductors, you cannot buy any capacitors, real capacitors like ceramics. In UHF, that's a good warning to you. If you open up a UHF antenna and it's got ceramic capacitors, I can tell you right off the bat, it's not a good design. Or little inductors, it's not a good design. You cannot produce, or you cannot purchase ceramic capacitors that are really good up to 500 megahertz consistently. You put them on a network analyzer, at HF you can, but up to even 50, 60 megahertz, you'll start seeing the series inductance part of it, the series resistance for losses, and also going past the self-resonance. These things will have self-resonances because that capacitor will have a parasitic inductor in parallel with it. Or similarly, the inductor you buy, it may work fine at 30 megahertz. You know, whatever, let's say you buy a 30 nanohenry one. It doesn't stay 30 nanohenry at all frequencies, maybe low frequencies, because as you go up, the capacitance of the turns starts coming in. It has a self-resonance. So I figured, no, forget this. No inductors, no capacitors. Not at the frequencies we're dealing with. And you can probably make HF traps, but you can't make, it's hard to make traps up at UHF. You can make one for yourself, but to publish in an article and for them to go buy a 100 nanohenry chokers and forget it. It'll be so off. And then the capacitance and self-resonance. So, okay, none of that stuff. So I tried all types of configurations, and I'm going to show you what I did, and it's been very successful. I did, 35,000. It's not bad. It could be one of the most popular VHF, UHF antennas out there, mainly because it's pretty inexpensive. So here I showed you the pattern. Again, if you use a 2-meter antenna at UHF, vertically, 75% of the energy goes in the air. You can't afford that. That's all of a sudden your 4-watt handy talkie looking like a 1 watt, right? You don't want that. So again, one thing you got to understand here is the Smith chart. You don't have to understand all the details. We spend probably 3-4 weeks in graduate school teaching the Smith chart. But all you have to accept from me is, if you have a quarter wave stub, depending on the frequency, quarter wave at UHF is about 5 1/4 inches, 5 inches or so. That means at this size that you see, if I short circuit one end, and at that frequency, 445 megahertz, and put a network analyzer on the other end, it will read a very, very high impedance. It may not be infinity, but pretty high. Similarly, open circuit, like an open circuit, you read it on the other end, so, well, if it's open circuit on one end, shouldn't it be open circuit on the other end? No. That's DC. You gotta break away from that. No. If you go quarter wave, in this case, 5 inches at about 445 megahertz, then open circuit on one end, it's gonna be a short circuit. And I don't know how many of you caught this. I said about 5 inches. Typically UHF, you see, isn't that 6 inches? It is, in air. Right? In coax, it's going to be about 20% shorter because of what's called the velocity factor. Remember, how is this dimension determined? Quarter wave, 5 inches. It's a very, very important formula in antenna design. C is always equal to F lambda. That is, the speed of light is always equal to the frequency times the wavelength. So that means in air, the speed of light is 3 times 10 to the 8th meters a second, equals to, let's say frequency is 100 megahertz. Lambda is going to be 3 meters, if you work out the math. 3 meters, so 100 megahertz is 3 meters. In air. But if it's in coax, that's not in air. The speed that the wavelength signal travels from one end to the other is not 3 times 10 to the 8th meters a second. It's about 20 to 30% slower because of the dielectric. So when you use the formula C equals F lambda in coax, you cannot use C 3 times 10 to the 8th meters a second. We use like 2.5 or thereabouts, depending on the characteristics of the coax you're using. Because that's how much it slows down. Then, if it's the same frequency, then lambda is no longer, for example, we use 100 megahertz, C equals F lambda. C is 3 times 10 to the 8th meters a second. Frequency is 100 megahertz, lambda will be 3 meters. That means in air, a wavelength of 100 megahertz is 3 meters. If you're going to cut a piece of coax to, let's say, half wavelength for 100 megahertz, or let's say wavelength, it won't be 3 meters. Because you don't use 3 times 10 to the 8th meters a second, you use like 2.5. So instead of 3 meters, it's going to be about 2.5 meters. It's going to be shorter. So you have to remember that. You always have to compensate for the loss factor. So if I convince you of this, so how does a J-pole work? A basic J-pole. By the way, you guys can get these slides. So a basic J-pole works like this. Now this is a twin lead. It doesn't have to be twin lead. This could be easily just a piece of wire. The reason why that wire is there is because you cut it here, so it's just kind of floating. This is a half wave, 37, 38 inches. So normally you would have center fed it. But hopefully I've convinced you that, not that that doesn't work, but from a practical point of view, try to hold an antenna at 90 degrees and far out there in the mountains on a repeater. It's hopeless. I tried it. It's hopeless. Because, again, you look at this picture of a dipole. You would like this thing to go farther and farther out. The further out you get it, the more ideal pattern you get. But then the longer this arm becomes, right? You guys can know this just from living, right? If this thing gets too long, you can't hold this. It's R cross F. It's the weight times the distance that gives you the force here. But you would love this to go further and further out. But the further you go out, the less durable it's going to be. And you want it to go further out because you don't want this to act as a reflector. So there's too many compromises there. And I know commercially they make dipoles, but they're welded. They're not soldered. The solder just will not hold out there. So what you do in this, so we give up on this idea of trying to feed it in the center, even though it's low impedance, high current, low voltage. Great, but it's just not very practical. Where's the best place to feed it is at the end. But at the end, it's high voltage, low current. That means it's high impedance. How do you make the impedance transformation? Well, it turns out some clever guy, I guess in the 60s or 70s, whenever, back 20, 30 years ago, said, oh, I know how to do it. We'll make a transmission line transform. That is a quarter wave shorted stub. A quarter wave shorted stub at 2 meters. Again, 2 meters quarter wave, 18 inches. In twin lead, it's more like 15 and a quarter plus 1 and a quarter, 16 and a half in that range, depending on the company. So it will be shorter than the standard 18, 19 inches you're used to, because it's in the twin lead, it's got plastic, it slows down the speed of light. Turns out this is pretty good. Do a short circuit at the bottom, go up a quarter wavelength, in this case about 16 and a half inches. It will be a high impedance. It's just a Smith chart. Short circuit, quarter wave, it's an open circuit. Well, then that matches the tip of the dipole. It's also high impedance. And lo and behold, you figure, well, if this is a short circuit, 0 ohms, and this is high impedance out here, ideally infinity, but probably not infinity, but pretty high, must we have crossed 50 somewhere? Right? It doesn't go from 0 to infinity without crossing 50. Turns out you do, at about 1 to 1 1/4 inches. Like 50 is probably closer to a short than to infinity. So yeah, it makes sense. Right about here. Coax there, and lo and behold, you've got a vertical antenna that's end fed. You can hold it from the bottom, and it won't be a lot of force. And again, if you put it in a PVC pipe, you hold it from the bottom, this thing lasts forever. So if you're convinced this works, well, this will give you that pattern right here. And if you use that antenna on the third harmonic, it gives you this four-leaf clover pattern, which is not the most ideal. It won't blow up your radio, but it will lose you 6 to 8 dBs, or about 75% of your power. So how do you change that? Well, first of all, here's the standard J pole, and there's variations of this, right? There's this, probably you guys seen the copper J, when they make the transmission line out of copper pipe. Here's the half-wave version, half-wave antenna vertical. Zoom in on this. This is the short circuit. So you tap it off here, and that's 50 ohms. And that works. In fact, we have built these. I haven't built one recently in our lab, but we show it. The students are pretty convinced that we can build it. Again, it's soldered. This is all soldered. It's not welded. If you want something to really hold up well on the mountain, it should be welded. Again, these dimensions are okay for 2 meters. You're kind of pushing it to the limit because of this T here and this elbow. I think I measured the center distance about not quite 2 inches, about 1 7/8 inch. So at UHF, the problem is this is a lot of exposed antenna for UHF. The problem with using this antenna at UHF, it starts radiating too much here. So I wouldn't recommend this for UHF. I certainly wouldn't recommend it because you can use the third harmonic, you can get those lobes again. But it will, I think it will resonate. It's okay. But certainly not at the UHF. You start getting a mismatch and the performance will be quite poor. And then here's an arrow antenna. This is trying to attempt to make a dual band. So this is single band. So arrow kind of had a little clever twist in this. They made a J-pole at UHF in parallel with a J-pole at VHF. They kind of made a single feed down here. And this sells, I don't know what this sells for, it's probably $70, $80 now. And I have one, I mean, it's made quite well. And it works okay. We didn't build this. I figured for 50, 60 bucks, I'll just buy it and try it out. I think it still suffers the problem. So the VHF resonance is here to here. UHF resonance, they have this extra piece here. The problem is it's single feed line. So that still, when you feed it, at VHF, this won't resonate, but it will resonate with the VHF, it's fine. At UHF, this still resonates at the third harmonic, and then you have the UHF antenna here. So at UHF, half the energy effect goes into here, the right antenna, but the other half still goes into the wrong antenna. So I think it's an improvement, it seems to work. The matching, you could probably play around the matching, but the matching is not the greatest. But it's pretty interesting antenna. Let's see, another antenna. Oh, just to mention, since we're on the topic of the J-poles. Have you ever heard of a Slim Jim? People mention this thing called a Slim Jim. It's really meaningless. They call it Slim Jim the twin lead antenna we have, and you just solder the tips together. In other words, somehow this got out on the internet that if you solder these two together, since this is a free floating wire, one has solder it, and they claim 6 dB of gain. There's no 6 dB of gain. It doesn't seem to do it harm, it doesn't seem to do it any good. So just squelch that one. Okay, so we move on here. So how can we make a dual band? Here's how we make a dual band. First of all, why does it resonate at 2 meters at UHF? I did the plots here. At VHF, here's the voltage plot for VHF on the stub. Obviously, short circuit 0, and it reaches its peak 1/4 wave. That's why it's called a 1/4 wave stub. High impedance means high voltage but low current. So here's the voltage wave here. If you measure the voltage along this line of resonance, like this, obviously 0 at short, it'll go a peak right after a quarter wave. If it peaks at voltage, it's got to be low in current. In other words, that impedance at that node is high, which is exactly that ends of the half-wave guide path. Now what happens at UHF? Why does it resonate at UHF, this stuff? Without the math, you can explain it. It should make sense. You start out with the short here, short circuit. If you go up a quarter wave, in this case UHF, about 5 inches a quarter wave. A quarter wave, it goes up to a peak. It peaks right about 5 inches. Peaks. But the thing continues. It goes back down in the Smith chart, another quarter wave, it dips. And then another quarter wave, it peaks again. So it hits a peak again. So even though it's covered an extra half wave, it hits the peak on top of the half wave. On VHF, you don't have that half wave. It's just a quarter wave. So in both cases, that node there is high impedance when you feed it down there. So it matches. That's why it matches. I'm not getting into the math. Now, the question is, how do you get the antenna to work? At UHF, the signal here, what would it like to see? It doesn't want to see the 36, 37 inches. It wants to see 11 to 12 inches, depending on where you have it registered. 11, 12 inches. So in this case, at 11 1/4 inch, you want it to stop. You want to stop. Because if it doesn't stop, what happens? If it doesn't stop at 11 or 12 inches, the current wave is going to continually go on. If it stops, you get a half-wave radiator, a half-wave pattern. If it doesn't stop, like in this case it won't, the currents continue. They continue out of phase at that point. See? If you look at this, take this point here to here. If it's UHF, the pattern will go like this. A half wave will stand on, because that will be a half wave dipole. But if you didn't end it at 11 1/4, 12 inches, it will continue the currents. That's why you see the angle radiation, those lobes start producing it going up into the sky, because this is pulling up that original wave ideally you had, but since you didn't cut off that piece, it starts pulling, the currents start pulling that wave from up, and that's why you get those lobes. But how do you stop that? You stop that by putting a quarter wave. These quarter wave tricks, these are really handy. I tell you, use that all the time. You take a quarter wave stub. Now, RG174 has a pretty high velocity factor. In other words, it travels at maybe 70% the speed of light. So again, a quarter wave RG174. Now you can use RG58, it'll be a little larger. And RG170 was nice and light. It's about 4 1/4 inches short circuit stub. Oh, I have one. I do have one. Hang on. I'll show it to you. Right here. RG174, thin stuff, nice and light, that's why I like it. You short the top. If you short the braid to the center conductor, that end tip will be an open. In other words, if you short the top, go 4 1/4, it's about 4 1/4 inches right here, 4 1/4, and it'll be an AC open. It's obviously a DC short, but at 445 megahertz, it will be an open. So when you stick a 445 megahertz signal through here, it goes through this routine here, this stuff, half wave and then a quarter wave it peaks. It sees this 11 1/4 inches AC wise. That quarter wave stuff short is an open circuit as far as it's concerned. At 445, it doesn't see this, stops the current, you get a nice half wave pattern. Now, VHF, that's not resonant anymore. Remember, this only happens during resonance. And this only resonates at typically 445 megahertz. At VHF, you're feeding the signal here, and that's the DC short. Goes high impedance there. That's not resonance. It just sees 11 1/4, 4 1/4, 17. Add that all up, and it's like 37, 38 inches. It sees the entire half wave. That's the trick in how this works. The stub is not a capacitor, it's a transmission line that you can fairly well control. fairly well. Much better than a capacitor or an inductor. And we also make a version, so you stick this into a PVC pipe. And by the way, if you look at these dimensions, here, these are the actual dimensions we use. We make the roll-up, which is designed just to hang up in air, not in the PVC pipe. Then the PVC pipe slows down the speed of light. Right? Nothing speeds up the speed of light. You cover the antenna. You stick this antenna into a PVC pipe, it's going to slow down the speed of light. Again, that means you have to shorten the antenna because C is always equal to F lambda. You no longer can use 3 times 10 to the 8th meters a second. You have to use something slower. So this is how you compensate this. Well, look at the dimensions. Here's the one we stick in the PVC pipe. Here's this roll-up version. Now I'll show you a roll-up version we have here. What's the roll-up version? I think some of you guys know what this is. It's for backpacking and emergencies. You just take it out of the pack. And it's basically, you unravel it. It's got a stub here that you don't quite see. It's hidden with heat shrinkable tubing. It's a well camouflage. But you just hang it up, and it's got a BNC connector, and it's also set to go. But it's designed to operate right in air. So the dimensions here, you do use 3 times 10 to the 8th meters a second, for C equals F lambda. So the one that goes into the PVC pipe, you've got to slow it down by about 4 or 5%. So you notice instead of, this is 17 inches to this piece, that goes in the PVC pipe. When it rolls up, that operates in air at 18 inches. In this case, the one that goes in air is 16.25 inch here. It's 15.25 in here. So you've got to shorten it a little bit because the speed of light slows it down. So the 2 antennas are not compatible in the sense that I can't buy a roll-up and stick it into a pipe and think it would work. If you did, you would lower the resonant frequency about 2 to 3%. You have to compensate correctly. It can be done, but they aren't completely compatible. Yeah, okay. And here's the results of it. If you look at it, using a standard 2-meter J-pole at UHF, you get this as a reference. And you stick an R antenna with that little stub, all of a sudden, boom, you get about 6 dB of gain left. That's quite a bit, 4x. But that says this attenuates quite a bit. You just cannot reasonably use a 2-meter VHF antenna at UHF and expect good performance. You have to modify it somehow to get decent performance. Again, the good news is it won't blow up your radio, but it's not the way to get good performance. You actually can, you would be better off using a rubber duck than a VHF antenna used at UHF. And we take these measurements. The student actually measured on this. Making official, we took 5 measurements on a foggy day, 5 measurements on a sunny day, and a rainy day. And these are the averages. And sure enough, the numbers are pretty good. Quarter wave mobile as a reference, minus 24.7. Our antenna, minus 23.47. So you notice, better off than a mobile by about 1 dB because it's a vertical J-pole. A quarter wave mobile, it's using the roof of the mobile as the other quarter wave. So a dual band J-pole, vertical J, does perform better than a quarter wave ground plane typically by about 1.5 dB. And we compared that to a rubber duck. Yeah, it was about 6 dB, just like what they say, it's about 6 dB. So rubber duck is not ideal for VHF. It's convenient, but not ideal. And a standard VHF J-pole is like our J-pole, pretty much the same. 3, like a 3, 4, it's within within 0.1 dB. Within 0.1 dB, good enough. Despite that stuff, it's a little bit of loss, but it's really, unless you have very sophisticated instruments, you would not be able to tell that. How about at UHF? Oh, at UHF does the antenna shine? At UHF, again, We have a quarter wave reference mobile, minus 38.8 dB as a reference point. You use a rubber duck, you lose about 2 to 3 dB, unlike 6 dBs. At UHF, you don't lose as much. Why? Because rubber duck at UHF is 5 to 6 inches. It's pretty close to a quarter wave. As opposed to VHF, that rubber duck's 5 or 6 inches, and it should be 18 inches. It's shrunk quite a bit. So yeah, it loses more gain also. If you were to use a standard J-port UHF, it's terrible. You measure it, it's terrible. Minus 38.8 is the reference. Man, you're down to minus 45. That's 7 dB, well, 6 dB loss. 6 dB down if you use a VHF antenna at UHF. Not a good idea. The only good news is it won't blow up your radio, but it's not a good high performance antenna. And if you take that little stub, that little clever stub we put in there, boom, it comes right back. Minus 45 comes back down to minus 38.9, which is 6 dB back. Just like that, just clever, simple, clever insertion. So it does work. Here's our lab. Here's our original lab. We did this in 2008. Now we have a more modern one. This is actually my house back here. We have one of these 5062 analyzers. But most of my students just use one of these really cool, sub $100 nano VNAs, 4 inches. Hey, I see the audience. Raise up your hands if you have one of these. Yeah, see, most of you guys have them. Yeah. I look at these in my classes, and that's, I'm not going to require you to buy a textbook, but I'm going to require you to buy a nano VNA. They're that handy. We're an RF guy. They're really, really that handy. Oh, here's some interesting pictures. They're looking at the stub. That stub I had should be infinity. So this is a swept from 30 megahertz to 1 gig. And at 445, so it never reaches infinity. High impedance, remember that's 0 ohms, it's 50. High impedance, so there is some loss in there. But it certainly still does its work. It's fairly high impedance. And it's pretty stable. I put my hand around and everything. That resonant part is pretty good. Again, it's not infinity. I didn't expect it to be, right? It's kind of has some loss. It's flat. See, here it is vertically. Again, that can stay up there for years and years and years. The vertical force you can withstand. If it had horizontal forces, then its lifespan is limited. So I like this idea. No DC lightning, the rest is a DC short. And all vertical force. What's the trade-off? It's got 3 1/4 wavelengths high. So, at VHF, UHF, it makes sense, this configuration. At HF, it does not make sense. Too big, right? Because a quarter wave ground plane would have been like this, up to about here, and that's it, with radio. So this is taller, 3 times taller, but I think overall, its durability is much higher because it's all vertical force. Okay, our roll-up, we make a little kit. I think probably a lot of you guys have it. We got the antenna, we include a 6-foot extension, and we include these adapters. It's because it's got a BNC and the coax will go to BNC to SMA and flip it SMA female. And we sell this, we're gonna run out of supply. Right now I'm trying to work with suppliers. This tariff thing has really stopped our supply the last 60 days. So I had some backup, and I'm slowly running out. I had about 60 days of inventory. I'm running out, but we're working through some other suppliers. Hopefully they'll come through with this stuff. The Chinese are not going to send things over with the tariffs, not knowing what they are, because they've been changing every day almost. Hopefully we'll get some supply. But right now I've got enough. If you guys have to order a dozen or so, I've got enough for a dozen. So if you like this talk, here's my other talks. One is how do you get gain out of a linear J-pole, and the theory behind it. And then I also give one at 220. This slide's kind of obsolete. I'm just showing some, if you guys are into 220, some of these Chinese radios are pretty good. The Baofeng 220s, they don't cost very much. They seem to work. We give them away as raffle prizes, and we have pretty good luck with it at our meetings. And this is my favorite radio, except we can't get a hold of them anymore because of COVID. Not COVID, because of the tariffs. This is a USDX QRP radio. I really like this. It's an 8210 HF. Has a CWD code. It has bandpass filters, SDR radio. You know, it goes for about $155. I use mine all the time. It's really lots of fun. That's the insides. They're pretty well built too. Okay, so the last thing is I'm going to send you guys this spreadsheet, and it's 20% off the internet price. I'll send Adam or someone the spreadsheet. You guys fill it out. Tell me what you need. I'll just send me one check and I'll send it to you guys. You can distribute it. So it's basically 20% off. You know, our DBJ1 antenna I talked about today, number of retails for 55 here for 38. We also make a commercial version of that. Instead of ham, VHF, UHF, it's commercial. That'll cover murmurs and then GMRS, FRS. The roll-up, same thing. We normally sell that for 60. You guys get it for like 40, about 20% off. Again, we make both a ham version and a commercial version. The tri-band we didn't talk about today. I'd like to talk about some other time. That normally sells for 90. We'll sell it to you for 65 because you're part of the club. And if you're in the GMRS, we make that's that gain UHF antenna I was talking about. The most popular version of that is the GMRS version. Normally sells for 60 and actually sells for 65. Now we have to raise the price of that. 43 the members. And then some extension cables if you want some adapters. But yeah, I'll send you a spreadsheet. Take your time. We're in no rush. We're more in a rush now for inventory trying to get stuff shipped here. I mean, we have a lot of things that are made here. The SL239s are made here. The Twin Leads made here. The RG174 is made here. But some things are just made overseas. You just can't get them here. And that's where we're having some problems. Anyway, thank you for your attention. And I'll open myself up for any questions.
Cool. Anybody have a question?
I have one.
Any questions? Come on up.
He can probably hear you if you speak.
Yeah, my question is, can you paint the PVC? Will that affect
Good
the
question.
antenna?
Yes, you can. One of my students tried a bunch of different paints, but the one that works the best, because it's not with the particles, what they have is Krylon spray paint. We found that Krylon, no measurable effect. You can spray paint it, no measurable effect. Okay. Any other questions? Well, let me ask for a show of hands. How many of you folks have one of our antennas? Quite a few. Okay, a few. Well, if you guys want more, I'm sorry for the guys that already purchased it because I won't refund you the discount, but if you want more. I mean, we sell quite a few. We retail out about $250,000 a year. Now, it's not all hams. We have contracts for ATD alarms, we have police and fire and FEMA. And it's a pretty good income source for my students. Very good income source, in fact. Very reliable.
Just a comment,
Sure.
I have worked with JPO and the difference between the roll-up and the PVC pipe. I found it was about 4 meg difference if you put a roll-up in the PVC pipe.
If you put the roll up in the PVC, the resonance will go off, though.
Yeah, but the drop in frequency was about 4 meg that I found.
That's right. Exactly, right. It drops, 3 to 4 megahertz. It would, yeah. So yeah, you can't ignore the fact that one's going to operate inside PVC pipe and the other one's going to out in the air, right? They're not compatible, basically. And so in the final dimensions, it's about 3 inches difference. I think about 3 inches difference. It's something you can't ignore. Yeah, I'm glad you did that. So anyway, thank you very much for your attention. And it's probably 7 o'clock. So it's still time for you guys to have a meeting. Anyway, I'm welcome to questions. Aside from Tuesdays and Thursdays during the day, I'm at school sometimes, but I'm usually home. Give me a call at home, or usually I'm here with students working on antennas, or I'm working on them by myself. So if you have any questions, feel free to call. And if you like this talk, if you want to hear a talk on the tri-band or the game, just schedule me in. I'm usually about 6 months down the road busy, but I can certainly schedule it. I try to limit myself to 2 talks a month. Otherwise, I just don't have time to do anything else. I've got students, I've got a guide, teaches classes to teach it, things like that. Okay, you guys have a good evening. Thank you very much for inviting me out.
Thank you.
Thank
Hey,
you.
man.
Much appreciated. Guys,
I used to buy.
you're bye. To me, like that.
Recording stopped.
All right. Hope everybody enjoyed that. If you did, put it on 614. If you didn't, put it on 612.
Absolutely. Thanks, Adam, for lining that up and looking at that. And thanks for organizing the group buy. We'll look for that. I'm not sure how you want to handle that. You want to handle that by email, reach out to you, or?
Yeah, I'll check out email it.
Okay. If you found that very interesting and useful, please let us know via the signal report. Because that is very helpful. It helps us get feedback for how we program the next meetings. So that's a fantastic opportunity. I'd just take a quick minute and ask everybody, if you haven't renewed, to go ahead and throw your renewals in. The other thing I'd ask also is, if you know somebody that's interested in amateur radio, ask them to join our club. Don't be bashful. Ask them to join us and come have fun with us. Ask someone to join. That'd be the best thing. All right. Any other questions, announcements, or any parting comments? Other than that, I would entertain a motion to adjourn. So made. Seconded. Motion carries. Thanks, everyone.